So algebraically, I'll show you how we could do this. What we're going to do is we're going to pretend that we're, I guess, I don't know, I'm not sure. Hopefully Bill wouldn't be offended by this if he was to watch it on YouTube one day. But as Bill Gates, we're going to pick the biggest value. We're the largest part of this function. And that's what we're going to apply to the limit. So for example, in this one, the largest value that changes is x. These constants ones wouldn't change. So I could rewrite this as the limit as x goes to infinity of 2x divided by x minus 1 over x divided by x over x plus 1 over x. So I've divided out the largest, most significant thing in these in this fraction. What's going to happen now is I end up with a limit of 2 minus 1 over x divided by 1 plus 1 over x. Okay, as x goes to infinity, what happens to 1 over x?
Dies.
It dies, yeah, or it becomes a 0. Right? So both of these would go to 0. That's why we end up with 2 over 1. We would find an asymptote here at 2. Okay. So see what happens when you take the Bill Gates theorem and you choose the most significant part of this function here and divide out. Okay. Well, maybe we should be clear. It's still not. Oh, it is 10 after 9. So you're on your own. No, I'm just kidding. What do you think what will be the most significant of all the pieces there?
X.
Well, we can do better than x.
X cubed.
X cubed is the most significant part there. So see what happens if we divide all the terms by x cubed, right? What will we end up with when we simplify? Okay, so some people have figured this one out. I heard a few mutters of 3. It's tempting to think the answer is 3, but in this case it's not going to be 3. If I was to do this and divide out the highest function, I would be talking about x cubed. So if I divide by x cubed, then it's going to look like this once I've simplified. The limit as x goes to infinity. So the top piece is going to be 3 over x minus 5 over x squared plus 1 over x cubed. And the bottom is going to be 1 minus 1 over x cubed. So remember, a constant never wins when it's being divided by something that's growing larger and larger and larger. The constant just slowly shrinks until it approaches 0, right. So that means this is going to disappear or die, as it was put in one of the other examples. They're all going to lose to those functions x, x squared, and x cubed. Okay? On the bottom, same thing. That would lose out. 0 minus 0 plus 0. Oh, let me get my calculator. Oh, that's going to be 0. And then 1 minus 0, that's 1. So this limit is going to approach 0. If we were to look at it in the graphing calculator, there'd be a horizontal asymptote at 0, which is the x-axis. Okay, so, whoops. So building on this idea of the Bill Gates theorem and how we just knock out everything that's insignificant, there's 3 rules that we can come up with for figuring out if they're horizontal asymptotes or not. Okay, so they look like this. If the degree of the numerator, okay, that's the top of the fraction, right, is less than the degree of the denominator. So that's top is smaller than bottom. Oops, I'm going to run out of space here. If the top is smaller than the bottom, well, you keep dividing by a larger and larger and larger value, it's going to keep approaching 0 as we get bigger and bigger and bigger. So in this case, the asymptote or the limit is going to end up on 0, just like we saw in the last example. Okay, in the last example, the numerator is x squared, and the denominator, the highest power, is x cubed. So a cube is going to beat a square, and it gets worse and worse the further away we go. Closer do we, the bigger the numbers get, the closer as we approach infinity, the worse that gets, and the better that x cubed beats x squared. we also saw when they were equal. So if the bottom and the top were equal, then what would determine the asymptote or the limit? What do you think? Well, it's on the board, I guess, but we're looking for a shortcut here. The way we did it will work, but I mean ultimately we can. Sure, Lily. The 5/3 thing, exactly. So what did we say? What was significant about 5 and 3? All right, Danny, repeat it for us since you were the first one that said it. The leading coefficients. These are the most significant coefficients. So for example, we looked at this one here. These have the same, they have the same exponent. Both of them are x's, right? So that means as we go bigger and bigger and bigger, as I said, this is going to be insignificant. And only those leading coefficients would be, the x's would sort of divide out, and the leading coefficients would be all I'm left with, 2 divided by 1. So if they have the same exponents, we can find the asymptote with the leading coefficients. Okay. Now there's only one other case which we haven't looked at, and that's what if the top is larger than the bottom? So for example, what if it's like x cubed plus 1 over x squared? What do you think is going to happen as x cubed competes against x squared and these values get larger and larger? Does anybody win? Is there a tie?
X cubed wins.
X cubed wins, of course.
Every single time.
So what's gonna, if x cubed is winning this battle, what's gonna happen to it?
It's gonna blow up.
Blows up, which I guess if you're referring to infinity, that's correct. It's going to just keep getting bigger and bigger.
Explode.
So again, if you think about this, like I said, as being, this 1 is really not significant. It's kind of like we're talking about x cubed over x squared when the numbers are large enough. So when the numbers are large enough, that x cubed and that x squared would simplify. It's kind of like an x. As x goes to infinity, it becomes infinite. So if the top beats the bottom, there is no limit. It does not exist. It's infinite. Okay. So see if you can apply the rules here.
Could that one ever be negative infinity?
Could it ever be negative infinity? Yep. Yep, it would depend on the signs of the top and bottom, and that was something we discussed the last day. So hopefully we can clarify with an example that comes up here. So I'm just going to zoom out a tiny bit so it's visible there. Okay, so all 3 examples are there. Okay, you don't have to shortcut this. I mean, life is nice when you can do things easier, but you could always revert to dividing out the largest function, right? The one that's dominating, or you could try to apply the shortcut to these. Okay, so see what you can come up with for the limits as we go to infinity. Okay, so in the first example, what's happening here? Does the top or the bottom win, or is there a tie? Yeah, there's a tie in this one because they're both x squareds. So because I have an x squared on the top and the bottom, right, the leading coefficients will determine that it's going to be 2/3 for the horizontal asymptote. Okay? So again, these are insignificant the larger the value of x gets. That's why 2/3 in the tie situation, it would simplify to 2/3. Okay, what about the next limit? Is there a tie or does somebody win?
Bottom wins.
The bottom wins. So what happens when the bottom wins? It approaches 0. The bottom gets larger and larger. It starts to destroy the top. Okay. And what about the last example?
Does not exist. Wait.
0.
Yeah. Whoops.
Okay, so the bottom wins again. We've got x to the 4th and x cubed. So that means this one's going to win, and we would have a 0 then. If the bottom wins out, it's going to keep making the top smaller and smaller. Okay. So, what if we're dealing with radical functions? I don't mean like really fun, awesome, cool functions. I mean the ones that have square roots in them. If we've got square roots, then this is where thinking about it like Bill Gates, well, I'm worried now. Maybe I'm going to get sued one of these days for using Bill Gates' name applied to this. But you got to think like Bill Gates when you're doing these ones as you go to infinity, right? You can shortcut all you like, but at the end of the day, if you really understand how this works, you have to be able to say to yourself, well, if I was to look at this limit, I'm not sure what's happening. But one thing I know is that -2 on the top, not very significant when those numbers get massive, right? It's kind of like, how disappointed would you be if you won $10 million in the lottery and they said, oh, but there's a $2 service fee for printing your check? I mean, you're not going to be crushed by that, right? The more money you won, the less disappointed you'd be by $2. So what we could think of is, we're talking about the limit as x goes to infinity of 3x. What could we say about the bottom? Can we simplify the way we think about the bottom? Yeah, the bottom, that 1, again, it's like you just won $10 million, and I'm going to give you an extra $1 because I like your haircut. I don't know, right? But that extra $1 is kind of like, oh, gee, thanks, right? It's not that important to us once we've gotten big enough in the values. So this is the way I can think about this limit, which would be 3x over 2x, and if we were to graph it, we would find an asymptote here. It would be 3/2. So even though the bottom appears to have the larger exponent, there's a square in it, that's not the case because I take its square root. Okay, so see if you can work out what's going to happen in the next limit over here. Okay, so if you're on the right track, what can you throw out of this? What's not important to you?
1.
Yeah. So as x goes to -infinity this time, of x over square root x squared, okay, then really what I'm talking about is x over x. There's going to be an asymptote at 1. Okay? Everybody satisfied with that? Anybody dissatisfied with that? Someone's got to be fit. As soon as the teacher says, well, does anybody have a problem with this?
The negative infinity?
Well, the negative infinity is different now, right? What could go wrong now?
Oh, 0, x can't be 0.
Well, let's try some values and see if we're on the right track, okay? Let's try 1, okay? We put in 1, and we divide it by square root of 1 squared, so it's still 1, right? We're okay. But what happens if we go, we want to go towards negative infinity? Let's try some negative numbers. Like, let's try -1000 divided by the square root of -1000 squared. What's going to happen to that? Yeah, it's actually going to turn out, whoops. It's actually going to turn out to be positive 1000 when it comes out. So this graph, it's actually going to have, sorry? If it went to positive infinity, it would be 1. So the graph has 2 horizontal asymptotes. It's going to go like this, from -1 and +1. As I go towards negative infinity, it's down here at -1. As I go towards positive infinity, it'd be up here at 1. So this is actually, you got to put your thinking cap on a little bit because that negative sign, it's going to be -1. Okay? So when it's infinity, it's, usually 90% of our cases deal with infinity, but if there's a negative, that should make you say, oh, something's different here. I better double check that I'm not, going too quickly with my limit. Connor? Good question. We're on the negative side. All of our numbers are negative, so the top will be negative, but the bottom will be positive. As we go to the left, this is only asking for negative infinity. It is only -1. There is also a horizontal asymptote at +1, but that would be if we were asked for the limit as we went to positive infinity. Had the question been worded, what are the horizontal asymptotes, then the answer would be both positive and negative. Okay.